So in this lecture, we shall be talking about the pumping lemma for the context-free languages. Uh, and once again, as we had with the pumping lemma for the regular languages, that they are making sense if applied to the infinite languages. So same is the case for the pumping lemma for the context-free languages. So if we have some infinite formal language and we are asking a question about its context of its being context-free, and then this pumping lemma would make sense. If some language or if some formal language is finite, then it doesn't make any sense to ask if that language is context-free, because finite language is regular and every regular language is context-free language, because we have a regular grammar for every regular language with us. And as we did in the pumping lemma for the regular languages, that the statement of the pumping lemma was applicable in its contrapositive form. Same is true for the pumping lemma or for the application of the pumping lemma of the context-free languages. It is also applied in its contrapositive form because it gives us the necessary condition for a language being context-free. However, there is difference between the pumping lemma for the regular languages and that of the context-free languages, in the sense that the basic idea regarding the proof of the context-free language is coming from the structure or the recursive structure in the grammar, which is the generator. In case of the pumping lemma for the regular languages, the basic idea of the proof was coming from the structure of the DFA, the recognizer. So the pumping lemma for regular languages is motivated from the structure of the recognizer, and the pumping lemma for the context-free language is motivated from the recursive structure of the grammar itself, which is the generator. Okay, so let's see what are those recursive structures in the grammar that help us out in formulating this result. So consider a basic example. Uh, this is a grammar which has 5 variables and 10 substitution rules, and this is a grammar that is going to generate an infinite context-free language. Now we have got 5 productions in here. Sorry, we have got 10 productions in here and 5 variables. So let us consider a string over here. The string in this case we have is a square, b square, c square, d square, and d square. The length of the string is 10, and it is derived from the grammar, and this is the derivation of this particular string. At each step of the derivation, one of the production rules is used. So we would like to see the recursive structure that is responsible for the pumping lemma. So the thing is, let's have a look on the derivation tree or the sparse tree for this string on the next slide. And there we have. So this derivation of the string and this sparse tree over here, they are just compatible with each other because they are supporting one another. So I have my string a square, b square, c square, d square, e square, and this happens to be its parsing tree. So the thing is, if I look at this parsing tree, and along the longest path of this parsing tree, with starting from the root, which is the start variable, to any of the leaves over here, I can see that there is a repetition of the variable b along this path. Now, this repetition of the variable b helps us out in decomposing this parsing tree into 3 subtrees. Let's see how those 3 subtrees look. So, this outer subtree, it is outlined by the blue dotted line, and its root is the starting variable s. Then I have an inner subtree, which is outlined by the green dotted line, and its root is the variable b. And then I have got the middle subtree, which has the b, b as its root, And if we come down to certain levels, I can see that, okay, these are the leaves of the middle parsing tree, and one of the leaf of the middle parsing tree is the variable b. The interesting thing is that since there is a repetition of the variable b, and this repetition has helped us out in decomposing or in looking at the three subtrees of the derivation tree. The first appearance of the B serves as the root of the middle tree, and the second appearance of the B is one of the leaves of the middle tree. Not only that it is a leaf of, but is a leaf not only it is a leaf in the one of the leaves for the middle subtree, but also it serves as a root for the innermost tree. So let us discuss a bit about the yieldings of these subtrees and yielding of these subtrees and these subtrees themselves. There is okay. Leave or node. Okay. By the way, every uh, every vertex of this tree is a node, but then we have a certain name for this node. We call it as the root, and then we have a name for the extremities of these nodes, which are known as the leaves. Yeah, that is a good concern. Okay. And by the way, please do not put your attendance right now. I will ask you after some time. Upon my signal, you have to put your attendance. And secondly, Zainul Abidin from section A, you have not put your attendance in the asked format. Please look at the format and then put in your attendance in that thing. Thank you very much. Okay, and please do not write in your attendance right now. Okay, and yeah, fine. If somebody has a question, they can always raise their hands. So what is B? It is not a leaf or a root. So for the time being, the B is a node in reference to the entire derivation tree. But when I look at the middle tree, this variable B, it will serve as a root for this middle subtree, and the variable B over here, this serves as one of the leaves of the middle subtree. However, the same variable B appearing at the lowest, or I would say at the deepest level, it also serves as a root for the inner subtree. But the story so far, what I wanted to emphasize was that because of the repetition of this variable B, I am able to not divide, I am able to I am able to see three subtrees of the parsing tree. The middle subtree, which has the first appearance of the variable B as its root, it will keep on going downwards or deep till the time it has the appearance of another variable or the repetition of the variable B. And then the outermost subtree and the innermost subtree are formed accordingly. Okay, so I want right now to discuss the yieldings of these subtrees. Yeah, as discussing over here. So the first subtree is the middle one. Okay, now uh, since I know that this is the legitimate derivation of the string, the original string, which was a square, b square, c square, d square, e square. So and at this moment I am looking only at the subtree of the derivation tree. Well, this tells me that the variable b, first of all, yields bsd, since this is the first outcome or outgoing arrow from the B, it means that it is one of the production rules. And then I have got that this sentential form. Now this is known as the sentential form, as we have discussed earlier. Now this sentential form is giving me another sentential form. Over here I have used the replacement for the variable s, and then finally from this sentential form I get another sentential form. Over here the representation or the replacement for the variable d has been given. So the yielding from the tree or this middle subtree is that the variable b derives the sentential form b square b d square, or we can, yeah, and uh, which is also visible or apparent from the structure of the subtree as well, that the variable b is giving us terminal b, variable b, and then d square. So that was about the yielding of the subtree, the middle subtree. Okay. Then I have got the outermost subtree. Now the outermost subtree's yielding happens to be, of course, this is the derivation of the yielding, and it is applying the subsequent rules of my context-free grammar, which initially had the 10 productions. By the way, there is one remark that I have, and I'm going to discuss right now, and this remark is that if I have, when I'm looking at the, okay, please don't, no attendance right now. Naveed Gonda, please don't disturb. I mean, now you have written it, so I can't do anything about it. But for everybody else, please don't do it now. I will ask you guys later. It creates disturbance. Uh, Whenever I have this context-free grammar with me, I would want two things. First of all, I do not want to have any epsilon productions in it. And secondly, I do not want to have any unit productions in it. So as we have discussed earlier, that whenever we have to bring some some CFG into its normal form, so we remove some sort of simplicities which were like the epsilon productions and the unit productions. So we are going to do the same story over here. Whenever I have some CFG with me, I would want that, okay, there are no epsilon productions in it, those are removed, and there are no unit productions in it, those have also been removed, and I have an equivalent grammar. And another story is that if I have some context-free grammar that is generating an empty string, I will keep that thing in my mind and keep it aside and just simply remove that empty production from it. And that would definitely be the starting variable giving us the empty production or the epsilon production. Okay. So now I have with me the outermost subtree, which has the start variable as its root, and the subsequent use of the productions is giving me the sentential form a square b e square, which is also mentioned over here. And so this is just a symbolic way of writing that I am able to get the sentential form a square b e square from the start variable s, and this happens to be its graphical representation, which is also known as the subparse tree over here. And lastly, I had the inner subtree with me, which had the root as the variable b. And then there is a production in my grammar which says that, okay, b produces c square, and c square is the entire substring of the terminals. Okay. Now, when I put them all together, I would have all of the subtrees with me, and their production and their yieldings. So the thing is, I have the yielding S producing a square b e square coming from the outermost subtree, B producing c square coming from the inner subtree, and B producing b square b d square from the middle subtree. Okay, so that is just the summary of what we have been discussing so far. Okay, now I am going to modify this derivation tree. I will modify it. Okay, how am I going to modify it? Okay, if I look at the middle subtree, its root is the variable b. And this variable b is also the leaf of the outer subtree. So you can see that, okay, this is the common thing between the middle subtree and the outer subtree. And that commonality means that, okay, if this is, and that commonality is showing us, okay, that it is the one of the leaves of the outermost variable, outer subtree, and it is a root of the middle subtree. And if I move downward, I also have one thing with me, that this inner subtree has B as its root. Okay, what happens if I remove the middle subtree right now? I'm just going to remove it. And if I remove it, it would mean that B as a root of the outermost tree will stay there, but I will not have the rest of the structure. And I also know that B is a root of the inner tree. And instead of using this B, which is part of the middle tree, for the replacement of the leaf of the outer tree, I'm going to use the root of the inner tree and bring it over here. So I would have modified my entire derivation tree, and this modification will bring me to something new, and that something new is represented in the next slide. So I have removed this subtree and replaced it with the inner tree. Okay, uh, and it's a legitimate tree, derivation tree of some string, because look at the structure that I have with me. B is producing b square bd square, but at the same time b is also producing c square. So instead of using b producing the other thing, I am using the fact that okay, b is producing c square over here. So it's a legitimate string. It's a legitimate derivation or derivation tree or the parsing tree. Well, and then what happens to the uh, yielding of this tree? Well, the yielding of this tree is a square c square e square, and this is supposed to be a valid string.
Excuse me, sir.
GG.
सर हमने किस क्राइटेरियन पे मिडिल सब ट्री को रिमूव किया है?
Okay, let me get back. Okay, I think this was Yasin. Okay.
Yes, sir.
Okay, great. Uh, the criterion for the removal of the middle tree is that B appears as a leaf of the outer tree, and this needs the replacement, because we must know that the derivation tree of any string must have terminals at the leaves. If there is a variable at the leaf, it means that that derivation tree is not a legitimate derivation tree. As a matter of fact, we should not call it as a derivation tree, because derivation tree means parsing tree, and we do parsing for the strings. We do not do parsing for the sentential forms. Okay. Now I have b as a leaf, the variable b as a leaf of the outermost tree. Now I am looking for the replacement of this b by some sentential form that has all the terminals in it. One possibility is the use of the middle subtree, and another possibility is the use of the inner subtree, because both these subtrees have the variable b as their roots, and both can serve our purpose. So if I just leave it as it is, the yielding of the entire subtree is going to be the same string that I originally had: a square b square c square d square e square, the length 10 string. But if I say that okay, instead of using the root of the middle subtree, let me use the root of the inner tree. So this entire structure would be shifted to the to meet the leaf of the outer tree that is shown as in here. So the substring enclosed in the red line has been completely removed. So there is a guy asking me a question. Let's see. K E G.
Okay. Okay, sir. So the blue subtree is arbitrarily drawn.
No. The blue subtree is not arbitrarily strong. Achha, by the way, I have a question. If somebody from the audience asks me a question, is it audible to everybody?
Yes.
Okay, so great. So I don't need to repeat your question then. Okay, a good point, Sayyid Muhammad Akbar. Okay, you can mute yourself if your question is done. Okay, let me take another question from Irshad Hussain or Irshad Hussain. Just wait. Let me answer to this question, and then I'm going to ask you the. Okay. So this is not an arbitrary. This outermost subtree is not an arbitrary. The thing is, let me get back. First of all, I had some special string with me. If I start from the beginning, the string, where it is. This string a square b square c square d square e square, this is a special string. I have chosen it deliberately, or that guy Costas Busch has chosen it deliberately. The criterion for selecting that string will be explained later. But then the thing is, I have a repetition of the variable b along the longest path. Now this repetition of b is helping me out in creating three subtrees. So it is not arbitrary. The presence of the repetition of a variable, that is going to give me, okay, what are going to be the subtrees, the outer subtree, the middle subtree, and the inner subtree. First of all, you create the middle subtree. The middle subtree is the subtree which has root as the first appearance of the repeated variable, and it goes deep till the time that another repetition of the variable b appears. And then you have the inner tree which has the second repetition as its root, and rest of the story is the outermost tree. So that is not arbitrary. So there was a question once again from Akbar G.
Okay, so like if the only criteria for making the upper subtree is the repetition of b, then a and e are also repeated.
Okay,
So why isn't a and e are the leaves of the upper tree?
thank you. Yeah, a very good question. Okay, so you can mute yourself, please. I am looking at the longest path. Now, from further discussion, you would see that maybe this is not the longest path. Let us see the length of the this branch. 1, 2, 3, 4, and the length of the other branch is 1, 2, 3. But look at the length of this branch that I am referring to, the longest path. 1, 2, 3, 4, and 1, 2, 3. Yeah. So length of the longest branch is 4. 1, 2, 3, 4. And the length of the other branches in which you are saying that the repetition of A or the repetition of E, their length is 3. So I have to look at the repetition along the longest path. Is it clear, Akbar? I hope that answers to your question. Okay.
सर एस भी तो रिपीट हो रहा है.
As we repeat, all right, fine. Now I have to look at the subtree. I could have chosen S over there as well. Yeah, there is a possibility that S is repeated and S can be seen. So we just have to see, okay, I have to choose a subtree wherein the repetition happens only once. And this is one story. And the second story is that S could have been chosen. Yes, you're right. S could have been chosen, but for the time being, I'm just considering B. So there is this is not the thing that okay only other than the starting variables would repeat. S can also be used as our middle subtree. Good observation. Okay, Irshad Sam, you had a question, or it is just by chance it's unmute. Irshad, you have a question?
No, sir, no.
Okay, okay, fine. Yeah, okay, great, good. Now, Umaid Zafar.
Sir, when S becomes the middle subtree, then all the middle tree will be all the nodes except the two C's.
Okay, in that case, I would have S, B, B, S, D. I mean, yeah, let me see if I can write something on it. I can annotate. Where is the pen? Yeah, I think there is the pen. Okay. The middle tree in that case would be this one. And how can I change color? Yeah. And then the inner tree would become
Sir, but the A and E are also children of S, just like small b and.
But do they appear along the longest path?
Yeah, but D is also part of the middle tree of B,
Yes, sir.
and
D
it's
and,
not in the longest path.
Yes, sir. D and small b.
What
They
do
are
you?
both not in the longest path, yet they are in the middle tree.
I'm talking about the red subtree.
Yeah.
The D is part of the red subtree, even though it is not in the longest path. So, like the latest blue subtree that you have drawn, A and E should also be part of that subtree.
No. They shouldn't be.
Why?
Okay,
Why?
they shouldn't be. Okay. Because I have to look at the production. I have to look at the connection between the repetition of the variables. Now the repetition of the variables is S. Now if you want this A to be a part of the middle tree,
Yes.
this A or that A.
Yeah.
No, no.
As D is a part of B.
As D is a part of B, okay. Okay.
There is no role of D being a part of B
Okay.
in the repetition.
Yeah. Okay. So what you're saying is that I could have chosen it in that way as well. Okay. Okay. This is a good observation. I will answer to it after some time. Good observation. Just keep a note of it, and ask me
So
this question
basically, it's
later.
arbitrary for the moment.
No arbitrary. No, it is not arbitrary.
Okay,
Just
so
yeah,
just the longest path and
just
B
the
is
longest
chosen
path.
arbitrarily. It could have been B or S, but we are choosing B.
Okay, yeah. Why are we choosing B? Yes, you are right. We could have chosen S as well. So you just have to select. For the time being, you can say that B was chosen. We could have chosen S as well. But then just give me some time, and I will make it clear to you guys why was the variable B chosen. Okay.
Sure.
Okay. Now that is. Let me close it. Okay. We have discussed this thing. Good. Yeah. So now we have the modified derivation tree, and it is giving us a new string, and that string is a square, c square, e square. And if I say that this string, which is as a matter of fact motivated from the original string, it is a part of the language. Would you guys agree? I've asked you guys a question.
It is generated by the grammar, so it should be the part.
Exactly. So since it is derivable from the start variable, so it must be part of the language. And mind it that it is motivated from the original string. Okay. Uh, we can also argue in another way when we say that okay, it is a part of the grammar. Okay, guys. Now is the time that you put your attendance. All of you, please put your attendance in the required pattern, and those who have placed their attendance before, they are also requested to put it again, because from this timestamp onward I'm going to see the presence or the attendance, and meanwhile I will continue my lecture. And if the time finishes, we shall be meeting again at 4:25. So let's have 15 minutes break between the two sessions. Okay. So I have three sentential forms with me in the derivation tree of my original string. S giving me a square b e square, variable b giving me b square b d square, and the variable b giving me c square. So when I look at the sentential form S producing a square b e square, this sentential form is going to give me a string till the time the variable b is not removed. Now I have got two possibilities for replacing the variable b. I could either choose the sentential form b square b d square, or I could choose the replacement of the b by the sub string c square. So if I choose the replacement of the variable b by the second possibility, I get a new string. And when I compare it with my original string, which was a square, b square, c square, d square, e square, I can see that, okay, this new string is just the original string, with the difference that it has no copy of b square and there's no copy of the d square. So, but it is part of the language, but it is a new string. So that is how I can say that the new string is part of the language. And the reasoning for the derivation of this new string is based on the fact that there were two possibilities for the replacement of the variable b in the sentential form of the outer tree. Now, since I have two possibilities, why don't I use the first possibility, which is the b giving me b square bd square? And in that case, once again, I have a variable b appearing over here. So why don't I just use this recursion again? And then after the second recursion, I apply the second possibility. In other words, when I draw it, I would say, well, A giving me this entire story, this B is replaced by the second sentential form, and then this B, once again, it is replaced by the second sentential form, and now the B in the second sentential form is replaced by the terminal C square. And as Akbar has mentioned it earlier, that this is all coming from the start variable. So this string is also coming from the start variable, and it is going to be a part of my language. And once again, I can see that the motivation for getting this new string is coming from my original string. And that motivation is entirely based on the sentential form b giving me b square b double d square. Now you can see that I have a repetitive pattern with me, and that repetitive pattern says that once you have b with you, you can replace it with the middle substantial form. So you do it once, and why don't you do it again? So if you do it again, you're going to have b square b d square, because this b is giving me b square b d square. So once that has been used, so I would have a multiplied by bb, once again multiplied by bb. So that would make a square b square whole square, and then b into d square whole square e square, and so on and so forth. And finally, if I want to terminate this derivation, I would have to use some substring of terminals, which is the c square in this case. So b is going to give me that thing with me. So now if I do it as many times as I may please, say for example 3 times, I would have a square b cube c square dd square cube and e square. So once again, I've got a valid string of my grammar. So now I hope that the repetitions pattern for getting new strings motivated from the original string is clear. So I have this thing with me. I had my grammar. This is some special string, and from the derivation of this, from the derivation tree of this string, there is a question coming.
Yes, sir.
Okay, Umar Farooq. Yes, please.
सर ये जो लास्ट पार्ट आपने किया है इसमें जो सी को जब आपने रिप्लेस किया तो सी स्क्वायर नहीं हो जाएगा?
Let me get back to the place. कहाँ पर? यहाँ पर?
ये जो थर्ड टाइम आपने किया सर. यस,
इधर है ना? यहाँ पर कह रहे हैं ना?
यस.
अच्छा अच्छा अच्छा, ठीक है, चले देखते हैं उसको जरा, यहाँ पर देख लेते हैं. वैसे यहाँ पर भी देखा जा सकता है. As I've discussed already that whenever I see a variable b, it has got two replacement. Either it is replaced by b square b d square, or it is replaced by c square. So at the first appearance of the variable b, I'm going to replace it by b square b d square. Once again, at the second appearance of this b, I'm going to replace it by b square b d square. And once again, I'm going to replace it by b square b d square. And finally, I'm going to replace this b with c square. So I'm not going to get a repetition of the substring c square. However, I'm going to get 3 repetition for the substring b square and 3 repetition for the substring d square. So that was the answer to the question posed by Umar Farooq. Okay, Umar? Can you guys unmute yourself? Umar?
Sir, okay.
Okay, okay, great. Okay, so let's move forward. So I can see that the pattern of getting new strings from my original string is coming from the derivation tree or the parsing tree of the string. And that pattern is telling me that I can repeat as many copies of B as I may please. But if I repeat B square I times, the substring B square is also repeated I times. So that was the point, the important point over here. I cannot have B square repeated 3 times, but D square repeated 4 times. I cannot do that because I do not have that freedom with me. The only freedom with me is to use this recursive sentential form or the recursion in this derivation of the sentential form. Whenever B is there, either you replace it by B square, B D square, or you replace it by C square. If you replace it by C square, you have no variables available with you. It is going to be the end of the story and the derivation would terminate. But if you want to have a repetition, so if you repeat B square, D square is automatically repeated. So in this way, I can say that I have this repetition pattern I have this repetition pattern in front of me. So this time you see that the repetition pattern is coming from the context-free grammar, which is the generator of this language. However, the repetition pattern in the regular languages was not coming from the regular expression, which was the generator. It was coming from the DFA. And we say that if our DFA has a cycle in it, then the language of that DFA is going to be infinite. Now, the same story is applicable over here. If I have a repetition of the variable along the derivation of the along the derivation along the derivation of the string, then that language or then that grammar is going to produce an infinite strings, and that language is going to be an infinite contextual language. Well, I will be continuing with this discussion after 15 minutes. So see you guys at 4:25. Okay.